when it comes to these material science innovations, and perhaps you've created something new, created something unique, how do you determine, how do you make the judgment call on if that's useful or if you need to maybe shift pathways and focus on something else?
This is a great question, and it's a question that material science professionals never stop asking themselves. I mean, Penny, David, we're presented all the time with ideas or different options for things we can work on, and we have to decide what to prioritize. Because one of the things you learn over your career is that even simple ideas, boy, they take a lot of time and effort to really realize. And material science is
Hello, everyone. Welcome back to the It's a Material World podcast. I'm your host, Puneeth, and joining me today is my co-host, David. What's new, David?
Not too much. Yeah, just returned from some travel, but I see you have a different background and you're holding your mic and it looks like you don't have a desk yet. What's happening there?
Yep. So as I mentioned before, I've officially moved to Chicago. So I'm recording from my bed right now because I do not have a desk at the moment. And yes, I am holding the microphone. So it's a little bit of a makeshift setup this go around and will be for the next episode as well. But hopefully, I have some travel coming up, and then after that, once I get settled back in, we'll have a regular setup with the new view and new background. So I'm excited about that. But yeah, moved to Chicago, really liking the city so far. Very close to parks and the river and everything like that. So super excited. But we have a longer episode today, so I want to get into that. We talk about energy transition with our guest today, Reed Eisenhart. And we really dive into kind of incrementalization, like incremental improvements versus disruption in the space, all of the platform technologies that come into play when it comes to energy transition. So I just wanted to ask you to see if you had any highlights from the episode. I mean, you have a batteries background, so I felt like this was kind of right up your alley, but I wanted to hear your thoughts.
Yeah, no, thought it was very interesting. He made a very big distinction about a disruptive technology where, for example, we could change chemistry or we could completely redo how like a photovoltaic is done or like just an incremental improvement and how that could be like just as influential in the greater scheme of things. And so I think overall he gives like a very good overview of the new technologies, but I think that he gives an update that these new technologies are actually pretty good. But I would say with all of them, they're in almost like the pilot phase to like the beginnings of their manufacturing. And so a lot of it will need incremental improvements to lower the cost, increase capacity, increase output, etc. And so it's on us to like try to like create the mass production of this view. And so I thought it was interesting to hear his point of view from it, as well as what he thinks needs to be done to get us to like full on green energy, reduce and fight climate change.
Yeah, for sure. I really liked kind of how he went into what was like the law of manufacturing. Just basically talking about how you can almost expect that the cost of manufacturing will continue to decrease significantly over a consistent period of time, like time intervals, which I guess it'll differ depending on the various technologies, whether it's batteries or photovoltaics or something else. But he really dives into that. And so it was really cool hearing kind of that overarching perspective. And I think he shares very unique insights that would be helpful for anybody, any material scientist, especially those who are interested in, the climate side of things, sustainability, alternative energy options. So we have a lot that we want to discuss in this episode. If you enjoy it, please leave a rating and review on your favorite podcast platform. And without further ado, let's get into it. Hello, everyone. So, for today's guest, I am happy to welcome Dr. Reed Eisenhart, independent consultant, energy transition technologies. Reed earned his master's and PhD in inorganic chemistry from the University of Minnesota, as well as his bachelor's in chemistry from the University of Kansas. After graduation, Reed began a 7-year career at Phillips 66 in the Energy Research and Innovation Division. starting as a scientist, then as director of the solar energy program, then senior scientist for batteries. Just recently, Reed started a new chapter as a consultant advising companies on energy transition technologies. Reed has developed expertise in the space, including batteries, photovoltaics, and biofuels. So thank you so much for agreeing to come on the show today, Reed. We're super excited for this conversation.
Thanks for having me on. I was thrilled to get the invite.
Awesome. Then let's dive in. We're super curious to hear about the context of your work at Phillips 66. It's very interesting to hear about one of the big names in oil and gas doing so many varied projects. Could you give us more detail about the specific projects and scope of your work during your time at Phillips?
Yeah, absolutely. So I went to the Phillips Energy Research and Innovation Center basically right out of grad school. I was recruited, and they were recruiting chemists and chemical engineers. And what the research center was focusing on at the time when I started, it was really exciting and it was collaborative and it was innovative. And our mandate was the company's vision was to provide energy and improve lives. And where that energy came from, they were pretty agnostic about it. So, the company had a long history in oil and gas. But if you look at the history of the company, it was really just about providing energy, and oil and gas became a dominant form of energy during the time that company was developing. So, their legacy installations were mostly oil and gas, but they were really interested in what's next. What's the future of energy hold? Where can we make money? If people want energy in a different form, why can't we give it to them? So when I started, we had a lot of different stuff. We had a big biofuels program. We had a big fuel cell program, a big solar cell program. Organic photovoltaics was the focus there. And a lot of other things too, like low carbon hydrogen and batteries. Eventually, we got really deep into batteries, and Phillips has a big battery business already, selling graphitic coke into the graphite market to make synthetic graphite for lithium ion batteries. We're a very big player in that area already. So it was a really fun place to work. It was cool how all these different areas of energy were kind of cross-pollinating. We were all learning from each other, having seminars together, developing IP, trying to develop new businesses. It was a really exciting place to start my career in the energy space.
So what motivated you to kind of transition from that role into more of a consultant in this space? And when did you feel ready to make that transition?
So that was this year that I made the transition. I had done a few different things. As you say, I had been the director of the solar cell group and then was a scientist in the battery group. And what I found was that I was gravitating more towards wanting to do the business development side of things and not be in the lab as much. And, as you get closer to business development, one of the things you learn in your career and you have to think about a lot is alignment with what the business strategy is or organizational strategy if you're an academic or whatever. And the willingness at recently for new business development in these spaces was kind of drying up a little bit. So I wanted to not hold back and wait for the company to want to invest in these new areas. I wanted to further my career in those business development spaces. So I decided to leave Phillips and go on my own. And right now I'm consulting with a sodium ion battery company. And that's going great. And just, I don't know what the future will hold exactly. It's, when you leave a company, it's, there's good and bad, there's pushes and pulls.
For yourself as a scientist, you've been jumping around. So you just said you worked on sodium ion, you worked on batteries, you worked on solar. While they have common threads, to have the expertise to consult, you have to have technical knowledge. How did you prepare yourself to jump to these different technologies and still be like an expert or be able to give guidance to others?
Yeah, that's a good question. I think my PhD was a really great foundation in science. It was just inorganic chemistry, just hardcore synthesis, spectroscopy. You kind of learn the fundamentals and then you see those fundamental things in everything, as you move forward. And material science is an interesting blend of so many sciences because a material is really complicated, and another thing about material science is no one is an expert on every single aspect of a material science project. Everything, it has to be very collaborative, and you have to bring together different skill sets. So, what I've found in my career is that if you have a good fundamentals, if you can learn quickly, which I do, if you know how to do research, book research or literature research, you know how to research the literature to get up to speed, and you work well with others, you can really get up to speed quickly. And sometimes, what I've found is the skill set that's needed on a team, you need different skill sets. When I was leading the solar cell team, I had some people that were just absolute technical experts, and I relied on them really heavily for different areas. But they weren't great to organize the group, or they weren't great at always knowing what the priorities should be, or other things like that. So, it takes different skill sets. For me, I've always been pretty good at kind of bringing everyone together, synthesizing all the different areas, making sure that everyone's heard, and that the project is moving forward with input from everybody. But definitely being able to use SciFinder and other things like that to go into the literature and look for the relevant references, and then kind of I like to write a report, put it all together, give a presentation, things like that. You can get up to speed pretty quickly, because a lot of times with these projects, it's all about what's happened in the last couple of years. You don't need to know like a 30-year history. Things change so fast. It's like, okay, where are we at today? What are the big problems that need to be solved right now? What's coming a little later? You focus on that.
Maybe you can help us kind of get up to speed a little bit, right, with this episode. So you kind of talked about energy transition and the technologies kind of in this space. And I think people generally might assume this topic is associated with clean energy technology, or, just an out with the old, in with the new approach, as you kind of mentioned, what's happened in the past couple of years. So can you just, to start this conversation, can you just briefly share what energy transition is in your opinion, in your words?
Yeah, absolutely. Energy transition is something, I'm devoting my career to at this point. It's something I'm heavily invested in. And it's really all about solving climate change and making a more sustainable world. And one of the things that I learned at Phillips is that people use a lot of energy, and people love energy. I mean, there are so many activities we do that are so highly dependent on energy. Flying somewhere, driving, boating, RV, so much of our energy, especially of our lives, especially in the United States, revolves around energy. We use a lot of energy. People love it. But we need to find a way to do that in a sustainable way. And we know that burning fossil fuels is not sustainable. We can't just keep putting CO2 into the atmosphere forever. So we need to have another energy transition, and we need to transition to an energy system that gives people more energy. It makes their lives better, and also it's cheaper, and also it doesn't have any CO2 emissions. So it's a big thing that we need to do. We need to transition our whole society, essentially, but it isn't unheard of. We've had other energy transitions in the past, and I had a quiz for you guys. This looks better on a chart, but I think I can describe it. So anyway, okay, so I have this chart, and on the x-axis is years, and it starts out at the year 1900 and it ends today. And on the y-axis, this is the quiz, is what is the units of the y-axis? So in 1940, it starts out at about 5 million a day. By 1970, it was 50 million a day. And today it's 80 million a day. So since 1970, it's only, not even doubled. But from 1940 to 1970, it went up 10 times. So what do you think the unit of that y-axis is?
Dave, maybe we can work together on this instead of it being a competition, but like thought
Okay.
is some sort of like consumption unit. I know that's
Yeah,
pretty vague, but I don't know. What do you think?
I agree. Sorry, you said it was 8 million or 8,000?
80 million a day
80 million a
today.
day. 80 million a day. A day. Okay.
It's crazy.
So here I'm gonna cheat, and maybe if I put it into years, it'll help me think of something. 80 million. So like 30 billion of some unit per year. I don't know if that helps you, but uh, yeah.
I have no idea.
Let's make an educated guess here real fast. I don't know. Gallons of gas. I'm not sure.
Gallons of gas. Well, you're on the right track.
Okay.
It's barrels of oil a day. And a
Okay.
barrel is
Okay.
42 gallons.
Oh,
So
okay.
right now, the world consumes 80 million barrels a day of crude oil. And that's a big number, obviously. But the thing I find fascinating is that 1940 to 1970, and if you look at the chart, it's basically parabolic. It's like totally smooth. And it goes from 5 million to 50 million in 30 years. It increases 10 times.
Wow.
And when you look at where we're at in the energy transition and with zero emission energy sources, we're at about 10% right now. We need it to be about 10 times higher. And people say, well, that's just, oh my gosh, 10 times higher. And you guys want to have net zero by 2050. Well, that's 30 years. Okay. We've done it before. We've done a complete energy transition in 30 years before. That was 1940 to 1970. And that wasn't just oil production. Okay. That's just the start of it. Oil production, that's the refineries, that's the pipelines, that's the gas stations, that's the roads, that's the cars, that's the garages.
Hmm.
It's everything. It was an entire way of modern life that was created over the course of 30 years. And that's happened before. It happened in our grandparents' lifetime. It needs to happen again, but with clean energy technologies. And it's going to happen. But we need to build a lot of stuff. And so that's going to happen during our careers. That's the really exciting thing, I think. And material science is going to play a huge role in that. You know, if you look back at that last energy transition, that was all petroleum engineering, mechanical engineering, chemical engineering, just pipelines and stuff like that. The new energy revolution is materials. This is electronics and technology taking over the energy sector through these platform technologies. And I want to talk to you guys about the platform technologies, and maybe we can get into that next. So what are the technologies that are going to play the biggest role in the energy transition?
Sure. So yeah, you said that right now we're at 10%. We need to scale up. Maybe to start with, could you tell us what technologies are currently leading the current clean transition?
Yeah. Yeah. And 10%, that was just to kind of get you started. So if anyone wants to check me in the notes or whatever, you know, basically we need us to be 10 times bigger,
Okay.
okay, in the next 30 years. The energy transition, there's a few really big platforms in the energy transition that are going to be part of that 10x in the next 30 years. And I kind of bucket them into three different areas. Generation, how are we going to generate clean energy? Transformation, how do we transform that energy so that it gives people energy where and when they want it, which is important. And then usage, how do we use the energy that's maybe different than in the past? And so in the generation bucket, we have kind of 6 technologies. Some of them I think are going to play a bigger role than others. The 2 that I think are going to play the biggest role are photovoltaics and wind turbines. Those are still growing very rapidly, and I'll talk about that later. And the technologies are still getting better. But then you also have hydro, which in the past has been one of the biggest sources of clean energy. You have biomass, which can be for biofuels or to burn it for electricity. Geothermal is one that is still developing, but it could play a big role, especially because it doesn't have as many intermittency issues as PV and wind. And then nuclear is kind of the big question mark, is how big of a play will nuclear play? It's up in the air right now. We'll see. It's definitely going to be in the mix. So those are our generation technologies, and where material science is going to play probably the biggest role there is in the PV space still. PV is still growing. It's still getting better. And I'll talk about that a little later, but material science has played a huge role in that. Okay, so now moving on to transformation, we know how to generate CO2 free power now. In fact, PVs are the cheapest source of power in the history of humanity right now, and they're still getting cheaper. So we know how to make the energy, but how do we get it to people where they need it and when they need it? I think the biggest technology there, and still the biggest one for us to keep developing as material science, is batteries. Batteries are going to play a huge role. And if you just kind of do a thought experiment, if you had a battery that was super cheap, super light, it would solve every problem in the energy space. You just have lots of solar panels, you charge the batteries, they'd be in everything. They'd be in your cars, in your garage, on the grid. All the problems are solved. But, it won't be that way. It's going to be a mixture of technologies because batteries won't be able to solve everything. Also in transformation, fuel cells and electrolysis. This is another big material science area, and it's, unclear right now how big it's going to be. But some applications are going to be hard to replace with a battery, especially like flying, like long-term or long-distance flights. For the foreseeable future, probably the best way to decarbonize that is with e-fuels or biofuels, and fuel cells and electrolysis can play a role there. You can also use electrolysis to make hydrogen from green energy sources and then use that hydrogen for all kinds of different applications. Okay, so last bucket, usage. We need to kind of change how we use energy. And so one of the big platforms there is our battery electric vehicles. EVs are going to play a huge role. Emissions from the transportation sector are pretty big. We're going to have to electrify a lot of that. Heat pumps, that's another big one. If you're not like huge into the energy transition space, you might not realize the interesting things that are happening with heat pumps. Most of our houses are heated with natural gas. Heat pumps are totally electrically driven and they're much more efficient. So one of the things that we're going to need to do as part of the energy transition is redo all of our infrastructure away from natural gas heating to heat pumps. And then the last bucket is just various industrial. There's a lot of emissions associated with industrial production of everything we do today. And there's going to be lots of different strategies to decarbonize those industrial areas. And then last one is aviation, and maybe aviation is an outlet for e-fuels or biofuels or something like that. So I think in a nutshell, those are the technology platforms. I'm a big believer that really what we need to do is just scale those platforms, make those platforms better. We don't necessarily need new platforms. I'm open to it, but I think things that are outside of those platforms are going to be kind of like connective tissue. It's going to be little technologies here and there to help that work with this and this work with that. And then that whole patchwork quilt is going to be our new energy system, in 2050. And we're all going to get to build that over the next 30 years. And it's going to be super exciting.
That is super exciting. And I appreciate you kind of laying out those platforms in a way that was easy to understand and visualize. And I like the analogy of the connective tissue with kind of the other technologies that might be interspersed there. Let's get into how we can make that happen. You said by 2050, and there's two types of material science innovations or genres, if you will, disruption versus incrementalism. Can you just kind of talk about what these two are and kind of go into the concept of the technology learning curve? Is that different from the kind of adoption curve or the technology adoption curve?
Mm-hmm. Yeah, I think it's especially when you're an early career scientist or you're a grad student or someone thinking about where they want their career to go. I wish that I had had an understanding of this when I started my career. And things have changed a lot since I, went to grad school in 2010. But I think students now need to have a really good awareness of where we're at. If they want to devote their career to solving climate change or something, they need to understand that the current energy technologies are pretty good and we need to keep advancing them. And sometimes people will muddy the waters, even professors will do it. They'll say, well, we need a new photovoltaic technology. We need a new battery, things like that. Okay, maybe we do, maybe we don't, but definitely just come in with a sober understanding of that. So that's what I mean by disruptive versus incrementalism. And I think academics and honestly, the US as a whole in the energy space is a little too focused on disruptive. For a long time, it has been true that the current technologies are not good enough to solve climate change. And, when you have 20 years of understanding that, it takes a long time, even for people that are really up on the space to kind of come around to, oh, wow, things have changed a lot, which they have. I mean, even in the last 7 years, things have changed dramatically. And it's all because of the price per watt or per kilowatt hour of these technologies. And really, it all comes down to cost because people want to use a lot of power and they have a finite amount of money. So it has to be cost competitive. We want the world to be, oh, well, everyone wants to solve climate change, so they're going to use less energy or they're going to do something that's not convenient. That just goes against human nature. That just isn't Some people might do that, but if we really want to transition the world, that's not going to be effective. But that's the incredible opportunity we have now, is that photovoltaics, wind, batteries, they've come down so far in cost that now they are the cheapest option. And not only are they the cheapest, they have really great benefits. I mean, battery powered cars in a lot of ways are superior to internal combustion engines. My battery powered leaf blower is so much more like better to use than the gas powered one. And same with the weed eater and stuff. I mean, it's great. So anyway, what has happened with prices and how did this happen? So I'll give you an example. So for photovoltaics, the price of a photovoltaic, solar has come down 90% in the last 10 years in price. It was something like $2 a watt when I started at Philips, and today it's something like 23 cents a watt. Battery prices have come down 90% in the last 2 years. When I started at Philips, it was, or maybe a little earlier than that, it was something like $1,000 a kilowatt hour. Today, it's pushing $150 a kilowatt hour. So how have prices gone down 90%? You know, in the oil industry, we didn't expect that to happen. You don't go into a meeting and say, in 10 years, this is going to be 10% of the cost that it is today. People would laugh you out of the room. If you don't understand the concept of the learning curve, if you don't understand the concept of the experience curve. And this is where technology, mass manufacturing meets energy. And these two sectors were always so separated that they didn't understand each other. Especially the energy industry didn't understand the idea of the cost curve. And so the cost curve goes all the way back to like the 1930s. This guy Wright, he was doing cost analysis of airplane manufacturing. And he was looking at all the different construction, the different manufacturing points in the aircraft production. And he realized that they were declining in cost or declining in time to manufacture in a really consistent way. And he put together a law of manufacturing. And it basically says that the cost or time to manufacture a unit is a function of the cost of the initial unit or kind of the first plant that you make times the cumulative number of those things that have been produced. And so if you plot the cost versus how many have been produced on a log scale, the cost goes down linearly. So as you produce more of something, you make it cheaper per unit. And it's very consistent. And you see this across lots of industries. NASA has tabulated it for many different things. They say in the aerospace industry, the decline per doubling of cumulative capacity, NASA says in the aerospace industry is about 50%. So every time you double how many airplanes are made, you learn how to make them about 15% cheaper. But then the next doubling is twice as big, right? And the next doubling is twice as big. So the slope on a normal, it looks kind of like, you know, it approaches a limit almost, but it never really does. And NASA says for repetitive electrical operations, the decline is even higher. It's 15 to 25%. And repetitive electrical operations, that's what batteries are. That's what photovoltaics are. So every time we double how many photovoltaics have been made, they decline in price by 20%. And that's what's basically been happening year after year since this technology was invented in 1970. It started out at $100 a kilowatt hour. Now it's 23 cents. And it's still declining. That's the incredible thing too. So if you look at wind, PV, and batteries, and you plot the data over time, wind is declining 13% for every doubling, and it's still doubling every 7 years. PV has declined 20% for every doubling, and it's still doubling every 4 years. Batteries have declined 25% for every doubling, and they're still doubling every 4 years. So it's predictable. In 4 years, the cost of producing a battery should be about 25% less. And demand is increasing. So we're going to see continued doublings of cumulative capacity for the next 10, 20 years. So it's a predictable decline. And in the energy industry, this is like mind-blowing. If you go to the computer industry, it's like, well, yeah, we always plan on the computers getting better. You know, they come up with applications and they say, well, computers aren't good enough for this right now. And then someone says, well, okay, Yeah, they will be in 4 years. So start developing it now so that it's ready in 4 years. In the energy industry, people just don't feel that gravity of technological progress, or they're starting to, but everyone needs to understand this is happening now. PV, wind, batteries, they're going to keep getting better. So when you see naysayers say, well, there's something about batteries that'll never be good enough, or there's something about photovoltaics, usually they're working on like 5-year-old data, and they're projecting that that's going to go into the future. First of all, their data is already super out of date, and they're not even understanding that this trend is going to continue to go down. I mean, if you really dive into these industries and the trade consortia that are part of these industries, they have plans on how to meet these price declines. I mean, you can look at it. They say, we're going to do this, we're going to do that, we're going to do that. We already kind of know how to do this. We're going to integrate it into the facilities. So these price declines are going to happen. But, one thing that's going to happen is raw material prices will fluctuate. So this is all about the cost of manufacturing, and it doesn't take into account raw material prices. But there's going to be fits and starts there where, demand exceeds production of raw materials, and then raw materials increase. But eventually prices for all these commodity chemicals will also come down as well. But there will be some variability in there. And so sometimes people can really build that up like, oh, cobalt prices are so high right now, and now EVs will never happen. Well, it's just a temporary thing. Eventually supply and demand will equalize, and those prices will come back down. That's just commodity material.
So yeah, that's great. I think one thing we would be interested about is hearing maybe an example from your experience on disruption versus incrementalism. And I think maybe another part is that so there's disruption in like a technology and then there's disruption in manufacturing. So I think we kind of shift from a technology point of view to how can we create this material in a new way as like the next step. Maybe you could talk about that a little bit more.
Yeah. Yeah, there's some really great examples in a lot of these spaces, and PV especially. So there are some like very incremental improvements that PV has been making to realize the cost declines per watt. And then there's been some more, I would call them innovations in the semiconductor device structure or the production process, like you say, that's more of an innovation than an incremental improvement. But all of it in the silicon space too, right? We're not talking about an organic photovoltaic or another different semiconductor. These are all silicon semiconductors. So incremental improvements in the PV space include wafer size and thickness. Basically, they're making the wafers bigger and bigger. These are like the blue squares you see on the panel. And as you make those bigger, it's less parts to manufacture per panel. It brings down cost. And they're making the thickness smaller and smaller, and they're figuring out how to manufacture those smaller. So then that gives you price declines. They invented something called a diamond wire saw that cuts these things with very little loss of silicon. So that's kind of an innovation, but also like year after year, they find out how to lose less like silicon dust. And then year after year, they figure out how to use less silver for the little connecting electrodes on top. So those are examples of incremental improvements, and all of that has to do with material science, working in the lab and figuring it out. And then, so the more innovative things is if you go back 10 years, the dominant technology for photovoltaics was P-type multicrystalline back surface field. So aluminum back surface field, that was the normal technology. And around the industry shifted over to monocrystalline silicon. So polycrystalline is the one that looks like there's like little crystals all over the place, and they're kind of like directing the light in different ways. Monocrystalline is just like very uniform, and that's because it's all one huge crystal that was like sliced up. So the industry has shifted to monocrystalline and P-type still, and then they're going to go to N-type. They're starting to transition over to N-type. And so those are different semiconductor structures. And, I have some cool figures here where you see a cross section, and it's all the different cool layers of different things and that they use to optimize things. And material scientists were like super involved in all that. And that kind of stuff is really cool. And then as you go on to the future, what is the future? This is going to be really neat to see if this happens. But, we're kind of maxing out or getting close to maxing out the solar cell efficiency for a single junction solar cell. And so if you want to keep increasing power output per unit area, one thing you can do is basically stack two solar cells on top of each other. One that absorbs low wavelength and one that absorbs high wavelength. And so there's been a lot of work in things that were originally called third generation solar technologies, like OPVs or other things like that. In the end, what's happened to those technologies is they've just been priced out. When I started in OPV, silicon prices were $2 a watt, and we said OPVs can come in cheaper than that, and we're going to undercut it. Okay, now silicon is 23 cents a watt, and no one is saying OPV is going to be cheaper than that. Or no one is saying perovskite is going to be cheaper than that. But what they are saying is, wait a second, silicon is so cheap that we can just use the silicon technology and we'll put our perovskite over the top of it. And that thing is still going to be cheap enough that people will want to buy it. And now it's going to have increased power output. So the industry is slowly kind of coming around to that. Some companies are starting to scale up what they call tandem technology, perovskite on top of silicon. We'll see if that takes off. That would be the next permutation. And there's going to be a lot of material science that goes into making that work. So it'll be fascinating to see if that can happen. And then there's another technology I just want to mention because it's an American company, First Solar. They make cadmium telluride solar cells. These are a thin film technology, and they're very competitive with silicon prices. And they have something like 40% of the utility scale solar market in the United States. And they're scaling up really fast, and they're hiring a lot of people. And in the solar industry, most of this is outside the US. So it's fantastic that First Solar is having so much success, and we'll see where they can go too. I mean, that is certainly a competitive technology to silicon in terms of scale and cost still. It's still cost competitive. So definitely give them support because they're an American company.
For sure. Well, thank you for that. I'm just curious with your consulting experience as well as, your experience with different technologies, when it comes to these material science innovations, and perhaps you've created something new, created something unique, how do you determine how do you make the judgment call on if that's useful or if you need to maybe shift pathways and focus on something else?
This is a great question, and it's a question that material science professionals never stop asking themselves. I mean, Penny, David, we're presented all the time with ideas or different options for things we can work on, and we have to decide what to prioritize. Because one of the things you learn over your career is that even simple ideas, boy, they take a lot of time and effort to really realize. And material science is complicated. I mean, you can have an idea to improve one aspect or one property, and it is not easy to change that one property without changing all the other stuff, you know?
Yep.
It's so hard. And then you have to go back and it's like, okay, well, how bad did I mess up all the other stuff? And then, how do I really push this forward and have a net increase in performance or whatever? So, it's something you learn over time. And I worked with that a lot when I was leading the solar cell team is working with younger scientists on like, okay, well, how do we prioritize what to work on? That's a good idea. Is it something we should work on right now? But one thing I wanted to talk about on this question is, first of all, and I've had this example happen so many times in my career, there's a saying, it says, you can save yourself an hour in the library with a month in the lab, something like that. So if you think you have a new idea, go on SciFinder, go on the computer, put a couple hours in, prove to yourself that that's really a new idea, okay? Because so many times I've had ideas, they were good ideas, and they were done 10 years ago, and to varying success. So, material science, these areas are not new. There's decades of literature out there. Make sure that you have a new idea. And then the second thing is, okay, you have a new idea. The thing you need to think about, and this depends on what kind of position you have, is think about your alignment with your organization. And that might be, okay, what is my professor trying to achieve? What is my professor interested in? Or if you're a young scientist at a company or something, what is my company strategy? What are they interested in? things like that, because this is so resource intensive to like bring a new material science innovation to the market, or even to publish a really good academic paper. And it takes a lot of people kind of stacking hands. And so you can't go it alone. And because you can't go it alone, you need to make sure you have good alignment with what the rest of your team is working on, because that's really how you go the farthest. And, it would have been really fun to be a scientist 100 years ago, when you could just go out on your own and just do something amazing and get a Nobel Prize. It's just not, I don't want to say it's impossible, but the low hanging fruit, a lot of it has been picked. And, we're in this stage in material science where things are very optimized. And, every once in a while, there's going to be like new paradigm shifts that come up. But for most of our careers and most of the work we do, it's a huge success if we can bring everyone together and kind of just push the ball a little bit forward, you know? So I would say make sure you have really good alignment with what your team is going after, because that's how you're going to have the most success. If you have multiple cool ideas, pick the one that's most aligned with what everyone wants, because you're going to find that you can push that one a lot further and you're going to have a lot more fun than trying to push against everybody else. That would be my advice on that one.
I know sometimes like once you have an idea, there is a lot of work to like fully realize it, and so it does take work to build it to what you want it before you can jump to the next idea. But with that in mind, like if we've taken a lot of this low hanging fruit, where do you think that the material science community should be focusing now, especially around climate change?
Well, I think, David, you might agree with me on this one, but I think, this is the battery decade, 2020 to 2030. This is the really hot area where we need the most material science innovation. PV is rolling. I mean, there's going to be really cool stuff happen in PV, but we don't need as much innovation in PV right now as we do in batteries. There's so many interesting things happening in batteries, and there's so many different use cases for batteries as opposed to PV. With PV, it's the use case is just like fill a field and let it sit there for 30 years, then do it as cheaply as possible. With batteries, it's like, okay, this battery moves, that battery doesn't move, this battery needs to charge fast, this battery doesn't need to charge fast, this battery needs to go in an airplane, this battery needs to work at low temperatures. So there's different use cases, and that's going to give rise to different chemistries, which will be cool. But also the fundamental chemistry is still changing really fast. I mean, just in the last few years, we've changed cathode chemistries considerably. We went from NMC as dominant now to probably LFP becoming the dominant cathode chemistry. There's lots of innovations on the anode side, in terms of solid state batteries, metal anodes, silicon anodes. And there's another incremental versus disruption is, do we just keep increasing the silicon content in graphite? That's an incremental improvement. Or do we go straight to lithium metal or something like that? Well, no one knows. Maybe we'll do both, or maybe we'll do one or the other. But there are so many material science problems to solve in the battery space. And another cool, thing that's coming up is not only making better batteries, but making cheaper batteries and taking this existing, lithium ion industry, which is pretty mature now, and we have a lot of manufacturing capacity. And how do we debottleneck that? So if we have a bottleneck and there not being enough lithium production, or not being enough cobalt or nickel or copper or graphite production, how do we keep making cheaper batteries? How do we keep fulfilling the demands of the market? And I think one of the exciting technologies there is sodium ion batteries, because it's as close to drop in as you can get to an existing lithium production. So you can use a factory that's making lithium ion batteries, and the vision for it is that, okay, you just change your cathode powder, change your anode powder, change your electrolyte, whatever, change a couple inputs into the factory and make some sodium ion batteries. And maybe factories are kind of, they're responding to market demands. They're making lithium sometimes, sodium sometimes, and they're maximizing their profit. I think there's a lot of potential for sodium ion batteries, but it's still very nascent. So it's going to be fascinating to see where that goes. And I mean, in all of these battery products, there's so many material science problems to solve, and there's going to be so many great opportunities, and there's going to be so much growth. It's going to be a cool industry to be a part of.
Can you just briefly go into the need for for sodium ion batteries and compare it to lithium ion batteries in terms of kind of what is the driver of sodium ion batteries from kind of resources, applications, the comparison of the performance between the two.
Yeah, absolutely. So if you look at the cost declines that have happened with lithium ion batteries, one of the big things that happened was the industry changed cathode chemistry from NMC to LFP. And that was really a cost saving measure in a lot of ways. Lithium iron phosphate is a cheaper cathode, and it got over some bottlenecks in nickel and cobalt production. Even within NMC, I mean, moving backwards, they slowly backed down the amount of cobalt in there to overcome bottlenecks. And then eventually they just moved all the way over to LFP in some batteries. So that was a way to realize cost declines. LFP, they're going to be able to ride that chemistry for quite a while as price declines happen. But, what will be the next chemistry that needs to come after LFP, if there needs to be another one to really realize even more declines? So one of the things I put together in this presentation that I'm looking at, just had a power outage, is that LFP, maybe could take us to $80 a kilowatt hour or something like that. I mean, no one knows. But today it's like something like 120. Maybe we can ride LFP down to 80 or something like that. But maybe we need a new chemistry after that. Could sodium ion batteries take us down to a $40 a kilowatt hour battery or something like that? That would be transformational in some ways, even if the battery is heavier or bigger or something, because it just goes to what people can afford. If everyone can have a huge battery in their garage, if the power plant can have a huge battery that's managing load, if you have a huge American truck with lots of area for batteries, you don't need the best battery. The battery could be huge in an F-150, and you could have a bigger battery, and people love it. People in America love bigger stuff. So sodium ion battery could be a way to give people more of what they want, more battery for the same price. And the reason that it could do that is a few things. So Albemarle has projections on lithium demand versus supply, and they think there's going to be almost 1 million ton deficit of lithium by 2030. And that represents about 600 gigawatt hours of battery demand, lithium ion battery demand. So that could be an opportunity for sodium ion batteries. And 600 gigawatts, that's not a small number. That's a huge industry in and of itself. So if the demand is there, and if sodium ion batteries are ready to roll, there's going to be a big demand for sodium ion batteries just because of the lithium deficit. And then sodium ion batteries have other ways to be cheaper as well. So they don't need a copper current collector. That saves cost as well. And then also the cathode chemistry, it's still kind of up in the air what cathode chemistry will dominate. But my bet would be the one that uses the least expensive cathode metals. So those are kind of the promise of sodium ion battery. Some of the manufacturers say it could be a 30% decrease in raw material prices. So that would, get you from your LFP prices down to your sodium ion battery price. And it's already being scaled up. I mean, and by big names. D, if you don't know, is the biggest EV producer in the world. It's bigger than Tesla in terms of output of EVs, and they're totally vertically integrated. I mean, they have like ownership stake in the entire production process of refining the metals, making the packs, making the cars, selling the cars, vertically integrated. They announced a vehicle called the Seagull with a price of $11,000, and it has a 30 kilowatt hour sodium ion battery, 190 mile an hour or 190 mile range. That's pretty cool. I mean, $11,000 car. I got a picture of it here. It looks like a fine little car. $11,000. Got a sodium ion battery in it. Who knows? Sodium ion battery won't just be for stationary. The downsides with sodium ion are gravimetric and volumetric energy density, a little bit lower than your lithium ion batteries. For gravimetric energy density, so the weight of the battery, it's pretty comparable to LFP, but about 15 to 40% lower than NMC type lithium ion batteries. Those are going to be your higher cost batteries. Volumetric energy density is where it suffers the most. It's about 50% of NMC and about 80% of LFP. So a car with a sodium ion battery, the battery pack isn't going to be a lot heavier, but it will have a bigger volume. So it might just be a bit wider or something. which I always joke, I live out here in Oklahoma right now. And, if you go ask a truck owner, hey, would you be sad if the truck was 6 inches higher? They'd be like, oh, hell no. They're lifting their truck up a foot already just because they think it looks cool. So we can get around the batteries being a little bigger. It's just not a big.
Yeah. I think I attended a talk at Stanford and they were talking about lithium. So for the entire world to become green, we would have to, by 2050, we would have to increase lithium mining by 15% year over year, every year. And like the maximum we've ever done it was like 12%, like a few years ago. And so I think that another promise is just that sodium ions are 23 times more like available in the Earth's crust. And so I think I agree with you a lot is that we don't have to have the perfect battery. It's like we can use sodium ion for some applications where space doesn't matter and we can just make up in volume. But like for some applications like planes or other things where like space matters, we can like pick and choose the chemistries a bit more. Right now I feel like lithium ion is just kind of the blanket statement. But so I think you do a really good job enlightening that. But maybe to wrap up the conversation, you can give us some parting advice for the audience on how our students can get involved or stay updated on the energy transition, and maybe just your final take on what we should be looking out for in the future as like students to be able to jump onto the next big technology or the next big wave.
Okay. Yeah. I mean, one advice I would have for students and early career people is always understand the context in which your lies. Understand what's happening in the field, kind of stress test the motivations that are going into your research, really understand how it ties in. If you're an academic grad student or something, it's okay if your project isn't going to be the next huge innovation that Tesla turns into a terawatt hour, scale industry. You are developing skill sets, you're developing expertise, but just have a sober assessment of it, saying, okay, I know this is, kind of silly maybe, or it's a real niche thing. In the introductions for papers, it can sometimes make it sound like this is the most important thing that ever happened in the world. Sometimes you have to write it that way for the journals, but just have an understanding to yourself, like really where it fits in and what the context is. Because in the energy transition, more so than in other areas, scalability is the most important thing. If you're in medical devices or something, you could make something that costs $1 million and you only have to produce 100 of them and they're really expensive to produce. And you might have a market for that. You might be able to make money on that. In the energy space, it's all about volume. It's all about, if someone wants to buy an EV, they need to buy 1,000 pounds of batteries. If someone wants their house to be powered by photovoltaics, they need to buy a lot of photovoltaics, or the utility needs to buy a lot of them. And so it's all about scalability, and very few technologies will ever get to that world defining scale. And that's okay. Understand that, and understand that, hey, it's a really good career if you're working in one of those sectors. If you're just contributing to pushing the ball a little bit forward, contributing to that 20% decline over the next doubling, that's progress. And that can be revolutionary, because after a few doublings and the prices go down, that totally changes the trajectory of things. As batteries decline more and more, they're going to change people's lives in ways they can't even imagine yet. And that's really the story of the energy industry, is you can make a huge impact on people's lives, but don't be afraid to embrace incrementalism, and always try to keep up on the latest in the sector that you're interested in. If you're working on OPDs, that's cool. I worked on OPDs for years, but train yourself on what's going on in the silicon PV space. Train yourself on what's going on at First Solar and CadTel, because when it comes to maybe trying to look for a job after school, those are going to be the areas that are hiring. And even if you want to go be a professor or something, a lot of professors, unfortunately, I will say, don't have great context on what's going on in industry. And I think that's unfortunate. So I hope that, if you want to go the postdoc and professor route, make connections with industry, keep a pulse on what's going on in the industry. That way you can make sure that the work you and your students are doing is going to be relevant and they're learning the skills they need, and hopefully making innovations that are going to make an impact in the world. And just know, in the energy space, it has to be scalable. And it's okay if your research project isn't scalable, but just understand that that's that's going to be the big hurdle for any innovation to clear, is that it needs to be it needs to win on price, and it needs to be massively scalable.
Well, thank you so much, Reed, for sharing that perspective. I think that was super important to share with our audience, and I appreciate all of the insights that you've shared, and even like visualizing some of the charts you had up as well for our audio only listeners. So really appreciate everything, and thank you so much for joining us today, Reed. It was a pleasure.
Thanks, guys. Yeah, it was fun. Thanks for having me.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.